Thank you. Thank you for this opportunity to speak. Our chapter is led by Sijme and Paardekooper, and our members consist of Paul Duffell, Frederic Masset, Gordon Ogilvie, and Hidekazu Tanaka. The ones that are from our team that are present in here, other than Ruobing and myself, is Tanaka-san. So when you have questions that we cannot answer, we will definitely deflect them to Tanaka-san. And so to start off, I'll let Ruobing give an introduction to our talk.
So planets are gravitational perturbers. When planets form in protoplanet disk, they can gravitationally perturb the material distribution and produce structures. At the same time, the mutual interaction between the planet and the disk can also drive the planet to migrate. So first, let's watch a few movies to help us visualize how this process looks like. So these movies are produced from hydrodynamic simulation. On the left, we have a 1 Jupiter mass planet, and once the planet is dropped in, the quantity being displayed is gas surface density. So it launches a few spiral density waves and gradually removes material from a orbital region to open a gap. And then the inner and outer gap edge become Rossby unstable and two large-scale vortices form. So spirals, gaps, and sometimes vortices are some of the most basic features of planet-disk interaction. They're not the only feature, though. Sometimes you get additional features. So in the example on the right, the planet mass is 10 times higher. It also opens a gap, but this time the outer gap edge becomes eccentric, and we have a eccentric gap precessing around the star. So in both simulations, the planet is on a fixed orbit. If we free the planet and let it migrate according to whatever torque it feels, the planet may move away from its original orbit. And this is shown in this classical movie, a planet launch density wave, and in this case, it goes inward. This is called planet migration. So just some very basic concepts. So a planet excites density waves at limit resonances, and those density waves exchange angular momentum with the planet as they propagate away from the planet. The net torque that the planet feels can drive the planet to migrate. At the same time, the planet may assemble a small circumplanetary disk around itself. So if nothing happens to those density waves, they will just happily propagate in the disk until they reach the edge of the disk. But if the waves are able to dissipate for whatever reason, then their carried angular momentum will be transferred to the local disk material, and that can cause gap opening and ring formation. So in this talk, Jeffrey and I will cover just three simple topics. Jeffrey will first provide an update since PP6 on planet migration. Jeffrey would also tell us our current understanding of circumplanetary disk formation from a theoretical point of view. And at the end, I will try to make connections with observations.
Okay. Here is a parameter space, a slice in the parameter space of planet migration. We have divided planet migration into a number of regimes, and I want to point your attention to these three particular dividing lines. Let's see if I can use one up here. This is labeled deep gap opening. This is the conventional wisdom that planets that open a gap and planets that don't open a gap may migrate differently. Although this particular division line, I would say that in the past few years has been blurred. And we'll see more details about that just in a few moments. Two other defining lines is this one. This is viscous saturation. And to the left of this plot, where you have lower disk turbulent viscosity, is the part that we have made the most progress since PP6. And within here, there is a fairly important notion called a feedback mass. And the planet migrates differently between up above this line and below that line. And the main difference in there is that a planet that reaches feedback mass can start interacting in a disk that has an effect on itself. So I'm going to start off with, I guess, the slightly more well-known parts of this parameter space, which is viscous type 1. So when you stick a planet into a disk, generally there are two types of interaction with the disk that we need to worry about in terms of planet migration. One is the fact that the planet launches these spiral waves, and there are density enhancements in these waves, so they exert a torque on the planet. And then another place that we need to worry about is the horseshoe orbits. This is also referred to as the co-orbital region. So within the co-orbital region, gas follow these lines. So they approach the planet, turn around, leave the planet, come back on the other side, turn around, and leave the planet again. And they're trapped in that co-orbital region and orbits with the planet. Viscous type 1 is the regime where the planet is too small to actually make a significant perturbation on the disk surface density. So it's just swimming in a sea of gas, not really making an impact on the gas much. And the resultant migration rate is just a competition, or actually working together between the wave torque and the horseshoe drag. The wave torque typically, almost always, pushes the planets in, whereas the horseshoe drag is a bit more complicated. It can push the planet out or in. And the substance of viscous type 1 was described in detail in PP6 under the chapter Planet-Disk Interaction and Early Evolution of Planetary Systems. And so here, I'm not going to give any more details than this, other than say that this is a very well understood part of planet migration. And all of this, in that chapter, I'm going to summarize with this single equation over here. So gamma here is the torque exerted on the planet. And then there is, and this is equal to a C, which is a numerical constant, and then is proportional to Q, which is the planet to star mass ratio, H, the disk aspect ratio, sigma, the disk surface density. And clearly, a lot of the physics is hidden in this numerical factor C. And C has been worked out to a great deal of precision. And if we know the disk properties, and specifically we are referring to something like the disk surface density profile, the disk temperature profile, if the disk is not isothermal, the disk entropy profile, and also the disk gas equation of state, is it isothermal, adiabatic, polytropic. If we know all those details, this parameter C, after a large body of literature that's been dealing with this, can be very precisely determined. And the result could be positive or negative. So viscous type 1 is not always inward. It can definitely be outward. And then moving along, we push the planet mass up. We go to viscous type 2. Viscous type 2 is when the planet starts opening a gap. And in the past, the idea here is that the planet opens a gap that is virtually empty. And because of the gravitational interaction between the planet and the disk is repulsive in this case, it's basically trapped, sandwiched between the two disks. And it can't really move unless the disk moves. And the disk does move because of viscous evolution. So the planet is pushed in as the disk itself flows inward. But in recent years, since PP6, it's been increasingly noticeable that this picture that I just described does not match simulations for multiple reasons, but the biggest reason of all is that the outer disk and the inner disk are not in fact separated. Gas is flowing, crossing the gap from the outer disk to the inner disk. And so there is definitely gas going around the planet, and you would argue that then the planet should feel all the same types of torque that you would feel in viscous type 1. Wave torques, horseshoe drag, all of that should exist. And so if I take the equation that I just showed you, and I replace the numerical factor C with -3, and then I replace sigma, that was the disk surface density, with a thing that I call a sigma gap, this equation would turn out to work really well in predicting type 2 migration rate. And sigma gap here is expressed over here, which is basically a description of how deep a gap a planet can carve. I'm not going to go into much detail for this equation, but Ruobing will talk about planet gaps when it's his turn, so I'll defer that to him. So this is really just looks like viscous type 1, except that in this case, remember that I mentioned you need to know the disk profile. Well, in this case, it is the planet itself that determines the disk profile. So I would say there's definitely been a paradigm shift in how we perceive the migration of giant planets. And fortunately, it is in a direction that unifies the picture and actually makes the answer a little bit simpler. So beyond that, we are going to go back down in mass and go to the lower left corner here where we have low mass planets and also low viscosity. This is where we need to worry about an additional thing called dynamical coortation torque. For type 1, so what this is that the planet essentially moves like viscous type 1, but with low viscosity. And low viscosity mainly in this case implies one thing, is that the co-orbital region that the planet has, this part that is trapped with the planet, as the planet migrates, that co-orbital region travels with the planet. That is not something that you could do if the disk is viscous. So over here we plot two simulations, one with high viscosity, one with low viscosity. And in the case of high viscosity, the planet is in the center here, and these streamlines of the gas, and you see these horseshoe regions. In color, what we show here is vorticity, or if you like, specific vorticity. And you see that there's no difference between the co-orbital region, the vorticity in the co-orbital region in the background disk. And that's because viscosity has diffused away the differences. So it's all just smooth. In the case of low viscosity, in this case, we see that in the co-orbital region of the planet, it has a higher vorticity. And where did that come from? Well, that's come from where the planet started. So the planet started at a place with high vorticity. It trapped that co-orbital region, and it traveled into a place in the disk that has lower vorticity than where it started. So when the planet is moving, let's say in this case migrating from right to left, the co-orbital region is behaving differently whether it is upstream or downstream of the planet. Up here, you have a trapped co-orbital region that it just continues to perform horseshoe turn, maintaining the vorticity that it had from where the planet started. And then on the other side, because the planet is moving, the gas comes in, and then it encounters the planet, performs a horseshoe turn, but then the planet moved away. So this stream never comes back. This is a stream that comes in from the background disk, performs one turn, and never comes back. So this is a turn that is performed by disk material at where the planet is currently located. So the material here is where it started, and this turn is where the planet is currently at. And because the vorticity up here and the vorticity down here do not have to be the same, generally disks do have vorticity gradients, that leads to an imbalance. And it's been worked out, and I'm just going to give you the quick conclusion here, is that if the trapped co-orbital region has a lower vorticity than where the planet is at right now, then that leads to a negative feedback on the planet's migration and slows down migration rate. And generally speaking, for protoplanetary disks, the vorticity profile is increasing inward. So if a planet is migrating inward, it starts off at a low vorticity region, moves into a high vorticity region. That leads to negative feedback. And so in that case, the orbital migration rate would slow down. And how much it slows down by depends on the total mass within that co-orbital region. More mass in there, the more it slows down. And theoretically, it could completely stop the planet. Moving up above the feedback mass. Like I said, this is when the planet starts to be able to make a change in the disk density profile. And that's exactly what this planet is doing over here. This planet is migrating inward, at the same time it's trying to open a gap. So this is kind of like shoveling snow. For those of you who do have to shovel snow, you would take a shovel and you push your snow, but then you need to shovel it further because you're walking toward the snow. So you go in toward the snow pile that you just created, and you need to shovel that on top of whatever is there. And eventually, you're going to build a ginormous snow mountain in front of you, and perhaps at some point, you're going to give up. And that's what happens to planet migration. The planets try to plow through the disk, it's trying to open a gap, and it creates a pile in front of itself. So that pile gets higher and higher, and eventually the planet just stopped, and in this case, it just stops and opens a gap where it stopped. And when it does that, you see that the migration of the planet, this is showing the position of the planet as a function of time. It goes in, and then it slows down significantly. Sometimes, in some cases, it seems to be completely stalled. So this is very nice in the sense that planets, maybe we don't have to worry about planet migration so much. Planets maybe they start moving and then they stop. It just stops themselves. It's a stable situation. Unfortunately, it's never that simple. When you take your viscosity and you lower the viscosity of the disk, more things happen than just the planet trying to open a gap. Specifically, you create vortices. Here is a simulation of a planet that is supposed to be undergoing feedback. Over here, this dashed line is what it would have done in physics if it were moving at viscous type 1's rate. And over here, these three lines are basically the same simulation with different resolutions. And you see that the planet is stalling, but then there's something happens here. It falls, and you don't get the same answer when you change resolution. The only thing that you know for sure is that they don't do viscous type 1. But what they actually do is actually unclear in here. And clearly, we don't even have convergence in resolution. We are not getting the same answer when we change resolution. That just means that whatever it's doing here is really hard to deal with numerically. And what it is planet-vortex interaction. Here's another plot that is similar to what we just showed you, but changing viscosity instead of resolution. And you see that in some cases, the planet do something, and then it actually migrates out instead of in. So what happens here is basically the planet, because it's able to make modifications to the disk profile, make bumps that turn into vortices, and the vortices collided with the planet and led to pretty fast stochastic migration that could be up or down. And then we also have, in this case, if the planet is very massive, it opens a gap pretty wide. You have a vortex that is pushed out pretty far. And in that case, it's a little bit less violent, and we see that the planet get pushed in a bit, but still in a way that is not fully understood. So I would say this is definitely a frontier to migration. So this is a quick summary of what we've learned. Over here, we know that the migration is determined by wave torque and horseshoe drag. These regions, we need to worry about planet-vortex interaction the most. Over here, you get nice feedback stalling, and over here, you get either accelerated or slow migration rate depending on the vorticity profile of the disk. So, so far, it would seem like that I've been dancing around the planet. I've been talking about these horseshoe. I've been talking about the wave. But what about the planet itself, that thing over there? Well, that's the circumplanetary disk. Here is our poster child of circumplanetary disk. I think this is going to be like a chow tao. We all have to look at it. So I have two things that I want to tell you about just in this talk. How large are circumplanetary disks and what shape are they in? So this is the quick answer to what shape they are in. Essentially, you get a disk if your gas is isothermal. If your gas is not isothermal, adiabatic gas is a ball. It's not really a disk, it's an envelope. And radiative calculations with reasonably realistic parameters also look like balls. To quantify a little bit about what I'm about to tell you about the size of circumplanetary disks, I want to point to you this parameter called the thermal mass, which is just the star's mass times the disk aspect ratio to the power of 3. And then I'm going to define a quantity called Q thermal, which is the planet mass divided by the thermal mass. And this is significant because subthermal planets, we need to worry about the Bondi scale. And for superthermal planets, we need to worry about the Hill scale. And the transition occurs somewhere between Q thermal of 1 to 10. This is the thermal, when you have an isothermal disk, one way to define the size of an isothermal disk might be to figure out where in the disk is actually rotationally supported. And if you use that definition for the CPD, you will find that for subthermal disks, the size is something like 5% of the Bondi radius. And if you think you might have heard me wrong, you're not mistaken. It is 5%. It is a very small fraction of the Bondi radius. And then if you're super thermal, then your disk size might be about 10% of the Hill radius. Oh, sorry. And then for radiative or adiabatic calculations, we have a disk envelope that is something like 20% of the Bondi radius for Q thermal between 0.1 and 1. There are more work on different parameter space, but I believe this is the one that has the most consensus in the literature. In this parameter space, the envelope size is something like 20% of the Bondi radius. So if you do that, if you believe what I just told you here, then maybe the idea of the circumplanetary envelope is not so different from what we thought about before. Because before, when we study gas giant formation, you would take a planet and you would model it like a 1D star, like a star, and then you just calculate the gas accretion rate like that. In this case, all that we need to worry about is it's still a 1D ball of gas, it's just the size is 20% of the Bondi radius. Although, I would have to tell you, unfortunately, again, it's not that simple. Because there's been a body of literature showing that if you take a gas parcel very close to the planet, deep inside that envelope, and you just wait, as it turns out, that parcel of gas will eventually circulate all the way back out beyond the Bondi radius, beyond the Hill radius, and all the way back out into this protoplanetary disk. In this particular simulation, after something like 1,000 orbits, the entire envelope of gas been circulated. That means that gas doesn't actually belong to the planet, and it has only a finite amount of time lying around the planet to cool. And this has very important implications on planet formation. If gas cannot cool, it essentially cannot accrete. And then another thing that I also want to point out is that if you believe what I just told you, then you might think you should expect to put a planet into the disk and you would get an envelope. But that can't be the whole story, because we have actual giant planets in our solar system that has coplanar, circular, prograde satellite systems, and that most likely formed from a disk. And even though I call them giant planets, actually the only superthermal planet in our solar system is Jupiter. Saturn, Uranus, and Neptune are subthermal planets. So they have to have a disk somehow, and if we believe that only isothermal gas can form a disk, then that gas has to be isothermal somehow. So that is definitely something that we still need to work on, and perhaps in PP8 we will have a chapter on satellite formation. So that's all I wanted to tell you about the gas around the planet, and now I'll let Robin talk about what happens when you try to look at them.
All right, so this part was briefly discussed in Zhao Huan's talk on Wednesday, so here let's take a more detailed look. So I'll try to address 4 questions in terms of connecting theory with observations. First, is this planet interaction capable of producing observed structures? If so, what kind of planets are behind structures? What can we learn about these planets from disk observation, and are observed structures really produced by planets? So first question, is this planet interaction able to produce structures? Well, let's see. Here are 3 images of the same disk, MWC75A. They're on the same scale, but at different wavelengths. The first one is a sphere in infrared scatter image, shows a pair of grand design arms at tens of AU. The middle and right panel shows millimeter and centimeter emission maps. This middle ALMA map shows a cavity, a ring, an inner ring and outer ring, and on top of that, 2 emission clumps. The northern ALMA clump has a counterpart in centimeter in this JVLE image. The southern ALMA clump does not have a counterpart here. The source centers on the star. These images look different because they're at different wavelengths, so they trace particles of different sizes. So these features may be explained using 2 giant planets. So at the bottom, we have 3 synthetic observations of this planet interaction models. They represent how we think planet-induced structures will look like in observations. So in the first model, We can see a multi-Jupiter mass planet on the outside can drive a pair of grand design arm inside its orbit in a scatter light, similar to the observation. The same planet opens a gap, and the inner gap edge is Rossby unstable, forms a vortex, collects millimeter-sized particles, and produce a millimeter emission clump. A second planet, somewhat less massive, a driven planet, is invoked at 35 AU. It too opens a gap and triggers formation of another vortex, produce another millimeter clump. The northern vortex is also good at collecting centimeter-sized particles, which is what we see here, a centimeter emission clump. The southern vortex is already in the process of decaying in this particular simulation, so it doesn't trap centimeter-sized particles as well, which is why we don't see a prominent clump here. So overall, these models roughly reproduce what we see in the observations. All right, what kind of planets are behind observed disk structures? The previous example showed giant planets, driven planets are able to do it. What about smaller planets? As it turns out, low mass planet as low mass as super Earths may be able to produce observable structures as long as the disk cooperates. So here I'm going to show you the surface density evolution of millimeter-sized particles in a disk perturbed by a 10 Earth mass planet. So let's start the simulation. The planet launches density waves and opens a bunch of narrow gaps. You might say this picture is somewhat different from the previous movies I showed. A planet opens a big wide gap around its orbit. This is because, first, this planet is low mass, and secondly, the disk has a very low viscosity. Alpha is 5 times 10 to the minus 5. It is 1 to 2 orders of magnitude smaller than the viscosity used in the previous simulation. So this phenomenon, a low mass planet opening multiple gaps in a low viscosity environment, has been explained in recent years. Long story short, such a planet can drive multiple density waves, and in this low viscosity environment, these waves can propagate, shock, and dissipate independently at different locations to open different gaps. So can we observe such a phenomenon in the real universe? Well, this is an ALMA high-resolution image of HD 169142. The outer disk shows a set of 3 narrow rings sandwiched 2 narrow gaps. And now this is a synthetic observation with a mini-Neptune mass planet at tens of AU in this disk, and it is able to produce this set of 3 rings sandwiching 2 gaps. All right, so what can we learn from these predicted planets in disks from disk observations? Well, intuitively, you might think the properties of the planet-induced gaps should change if we change the property of the planet. And if we can quantify the correlation between the two, there may be a way to infer the property of the planets from the observation of the disk. So in terms of the gaps opened by the planet, it turns out the gap depths in the gas depends on 3 parameters, planet mass, viscosity alpha, and scale height h. So such a semi-analytical fitting function provides a way to infer planet mass if we can measure the depths in the gas gap and if we know the viscosity and scale height in the disk. So similar techniques have been developed for other type of disk features. So here I'm showing you a movie in which everything else is fixed, but the planet mass increase. So as the planet becomes more massive, the gap becomes deeper, sure, and the gap becomes wider. The gap contrast increase, the gap become more prominent, and also more subtly, the separation between the primary and secondary spar arms increase with time. As you can see, they become more separated with each other. So all these correlations can provide ways for us to constrain planet mass, dynamic mass constraint. So that's good news because we want planet mass, right? But the not so good news is when we apply those to real disks, things are not that straightforward. Let's again take this one as example. So to apply this one, we need to know the viscosity alpha and scale height h in the disk. And as we have heard from talks yesterday, viscosity or turbulence level in disks are not easy to measure. And then to apply it, we need to know the depths in the gas gap, which is, again, another quantity not so easy to measure. Most of the gaps we see are dust gaps from continuous observation. And finally, there may be additional physics that we need to include in such considerations, such as thermodynamics in disks and MHD effects, because they may also affect how the morphology of planet-induced structures change. All right, if we ignore all this caveat for now and assume we have some idea of the disk parameters, we can make progress. So here are 3 independent works try to infer the population of protoplanets forming in disks. We're looking at planet mass versus semi-radial access. So this big color symbols are planets inferred from disk observation. Long story short, we're looking at Neptune to super Jupiter mass planet between, let's say, 10 to 100 AU. All right. Final of the four, are observed structures really produced by planets? Well, we have the PDS-70 system, a ring and a cavity and two accreting planets inside. Here is a synthetic observation with these two planets, and they are able to roughly reproduce the observation. So that's good news. But then again, the not so good news is systems like PDS-70 have been found to be rare at the moment. So many structures have been found, at least in big and bright disks. Here is a gallery we saw from Antonio's talk yesterday, and here's the ALMA D-sharp sample. Many of these disks have been targeted in direct imaging surveys. For example, in this one, here is a VLT sphere survey of 15 structured disks. And the schematics illustrate the kind of features. You get a few spirals and mostly gaps. So long story short, no new planets have been found, and in general, very few planets have been found in structured disks. So the meaning of that is still under, this non-detection is still under investigation. So to summarize this part, is this planet interaction able to produce observed structures? Yes. What kind of planet are we talking about? All the way from super Earth to basically the upper limit of planets, multi-Jupiter mass. What can we learn about those planets? Well, in theory, we can constrain their properties by studying the morphology of their induced structures. In practice, those efforts are sometimes complicated by the degeneracies in the models and our incomplete knowledge of the disk. And finally, are those structures really produced by planets? Some are, but direct confirmation have been scarce and difficult. So in my last 3 minutes or so, I would like to discuss where we move from where we are today. So on the theory end, one thing which I think is very interesting, and this is a recent trend that just emerged around the time we're writing the proposal, is the application. It's the application of machine learning in disk-planet interaction calculations. So in this field, we run simulation, and we run lots of them, and they are time-consuming. As it turns out, machine learning can actually help us dramatically reduce the computing time used in disk-planet interaction. So a few pioneering works have been carried out in the past really couple of years. And here is a latest example. So this is a tool developed based on neural networks. So it is able to make instantaneous predictions of the steady-state solution of disk-planet interaction in real time. So here, as you can see, the user is dragging those bars. So by doing so, he is adjusting viscosity, scale height, and planet mass in real time. And this tool can make predictions on the surface density of disk-planet interaction on demand instantaneously. This tool can also make prediction on velocities, which I didn't show. If you're interested, scan this barcode and you can play with it. This is also, of course, in the slides on Mattermost. So in terms of observations, I think two new avenues are worth exploring. The first is, I think it's time for us to move on from modeling individual systems, modeling individual observations at a single wavelength of certain systems. And instead, we should try to model multiple observations and multiple wavelengths of the same disk. And more importantly, those observations trace different structures produced by the same planet. So here is another edition of the planets inferred from disk observations from Jay Han's chapter. These blue dots, which is majority of those planet predictions, are made based on gaps and rings. And when Jupiter mass is here, so we see there are quite a few Jovian planets inferred from rings and gaps. Those planets, Jovian planets at tens of EU, are supposed to produce observable spiral arms. So these two panels shows synthetic observations of disks being perturbed by Jovian planet at tens of EU in near-infrared scatter light and millimeter continuum observation. You can clearly see the spirals. So for these predicted gap opening planet, are we really, can we really see the spirals produced by them? That's a test to the planet hypothesis here. So in the disk HD 169142, there was a planet candidate discovered a few years ago inside a gap in the scatter light. So very recently, Hammond et al. Rediscovered the planet, watched its orbital motion, and more importantly, in my opinion, they traced the spiral arm induced by the planet. So now we're looking at a moving planet orbital motion which opens a gap and drives a spiral. So this kind of more comprehensive evidence is perhaps more convincing than predictions made based on single type of features. And finally, we have new observing tools, right? So, and it will be interesting to renew the search of planets in those disks. So in James Webb, with James Webb in cycle 1, there's 6 disks being included in 2 programs to search for planets in structured disks. These 5 are included in a NearCam program, and these 3 are included in a NEAREST program. We have 2 posters highlighting their latest results, and I encourage you to take a look. Thank you very much.
Thank you very much for that talk. Time, 15 minutes for questions. So please queue up at the microphones, and we'll try to distribute yourselves around the microphones. Okay, JJ, I think, isn't it? Yeah, go ahead.
Yeah, wonderful talk. JJ Zanazzi, UC Berkeley. So I was wondering if you could talk a little bit about Feng Long's recent observation of dust pileups around the Lagrangian points of a putative planet.
Sorry, so which paper are you talking about?
So it's a Feng Long, I think it was 2022.
Okay.
Yeah, so what she found is they got continuum observations of a gap, and within the gap there was a putative planet, and around the Lagrangian points of the putative planets there was dust pileups that you saw in the continuum, and this seems like a really good probe of the stuff both of you were talking about, planet-disk interactions.
I'm not too familiar with that observations, but what you just described is actually a rather classical picture. When the planet is opening a gap, a massive planet, the Lagrange points, the triangular points, would accumulate material, and particularly is accumulating them in an asymmetric way. One of them would accumulate more than the other one. So if you do spot only one side, it is actually a theoretical prediction.
Thank you.
Just before we go to the next question, I want to remind everyone who hasn't voted for the poster to please do so. You have around 10 minutes, so please do that before we get to beyond the deadline. Thank you. Over here, yes.
Thank you for wonderful talk. Here.
Over there.
Yep. K. Tanaka, Tokyo Tech, and so I'm interested in the link to the multiple system formation. If you go up to the higher mass on the migration regime map, it will reach at some point to the binary formations regime. And where is do you know where is exact difference between the planet formation regime to the binary star formation regime?
I don't know, but then there's one thing that that Ruobing showed in his first slide, where when you have a 10 Jupiter mass planet that creates an eccentric gap, and actually that limit is more like 3 or 5 Jupiter mass. So once you go above that mass, the outer disk becomes eccentric, and the migration mode can become very, very different. I would say binary is exciting, eccentric outer gap edge is not at all a surprising thing, right? So I think that eccentricity would have a lot to do with how planets and binaries of that mass scale would migrate.
Great, thank you.
Okay, Guillaume.
Guillaume Leb, ANS de Lyon. So, as far as I know, those disks are dusty. And you haven't spoken too much about dust. And there have been a lot of efforts trying to do like multi-fluid simulation of dust and gas. So, could you give some comments about like what has been done and a perspective for dust and planet-disk interaction?
So some of the simulations we show are so-called multi-fluid simulation, like this one. There are both dust and gas, although the movie here shows the evolution of the dust particle. So in general, yes. In the past, I think, when we were starting this business, most of the simulations are gas only. But these days, more and more dust simulations are being done, particularly to be compared with the ALMA observations.
Geoffroy?
Yes. Hi, Geoffroy Le Sur, IPAC Grenoble in France. Thank you for the very nice talk. I wanted to say that it's really striking that the new models in PP6 now rely on very low viscosity disks. So I find it quite exciting, and at the same time I find it quite worrying because, for instance, if you want to explain there's very nice thin rings as you did, you need to rely on low viscosity disks which are by nature not accreting. And we know from talks earlier this week that disks are actually accreting. So don't you think that there is some tension which is telling you that you might be missing some important physical mechanism in there?
So that's an excellent question. So in simulations like this, we're tailored to be compared with ALMA dust observation, and for those observations, we're talking about millimeter-sized dust. So hopefully they have settled to the disk midplane. Therefore, those viscosity levels included are intended to mimic the midplane condition there, which hopefully doesn't have a lot of turbulence. So, and it's a fair question to ask, if you go beyond and say, what if you include MHD and have a disk with accretion driven by wind and with more or less quiescent midplane? Those are certainly good projects and to be explored. Yeah.
So accretion can be driven by turbulence, but also in some laminar version, like by winds. And within our chapter, we do have a discussion on migration in a wind-driven disk. So I invite you to take a look at that.
Okay, question at the back.
Andrei Zella from Rice University. Thank you very much for the nice review. I have two general questions about the migration and the torque. So one is, once you start to perturb the surface density of the disk, you change also the temperature by changing the illumination pattern of the disk. So you change the hydrodynamics. And so how does that affect your calculation in the torque? The second is, what happens if you have multiplanetary system? Because they are common, right? So the solar system, we have Jupiter, Saturn, and your torque is very sensitive to all these parameters. So your beautiful picture of tiles with different regimes, how should I figure that if you have multiple planetary systems, which are probably the most common system?
Thanks for the questions. Very, very interesting questions. For the first question, in the viscous type 1 case, we have done a very thorough study of what happens under various equation of states. So if you're interested in viscous type 1, then I think we pretty much have the answers there. And but in the case of opening a gap, like you said, I would say we know very little about what actually happens to the gap when we worry about equations of states that are not isothermal. And part of that is because you cannot just simply run a adiabatic simulation of gap opening, because when you have the gap, by definition, the planet is launching a shock. And the planet is, if you fix the planet's orbit, then that shock has an infinite engine, and it will heat the disk up indefinitely. So in order to simulate that, you would need to include some version of cooling, and that part becomes a big can of worms. You just don't know what is the realistic way of cooling the disk at the edge or inside the gap. Because of those complications, I think we are definitely coming up with ideas to try to deal with it, but there's no answer at this point. And then for the multiple systems, we do have a pretty long discussion on that in the chapter, so I would invite you to read that.
All right. Thank you.
Just to remind you, we've only got about 5 minutes left for questions, so try to keep the questions nice and short and the responses nice and short if we can. Over at the back over there, thank you.
Thank you very much for a very interesting talk. I'm Yuhito Shibake from University of Bern. So my question is about the circumplanetary disk of the PTS-70C. So PTS-70 system is already 5 million years old, and gas accretion rate is about 10 to minus 8 or 10 to minus 7 Jupiter mass per year. Then do you think the circumplanetary disk of the planet is already disk structure or still hot and envelope structure?
I don't know.
That's a perfect place to start.
But if it's going to form a satellite system, then it should have a disk by now. Yeah.
And is it possible to distinguish from the observation?
If you can measure the rotation,
Okay,
yeah.
thank you very much.
All right, over here.
Hi there, Philip Stansel, University of Georgia. So I have a kind of a naive question. I noticed you focused on the disk, but what about the planet? Can you track the rotation period of the planet as the disk evolves and dissipates? The reason I ask is that there's empirical relation in the solar system, right? The tangential speed of the planet is proportional to the square root of the mass, and is detected in some extrasolar planets as well. Is there any way that could be looked at?
Short answer is no. In all of the simulations that we have talked about today, the planet is treated as just a gravitational well. So there's no physical thing to turn or spin. I think maybe in chapter 20 we'll learn something about that. So.
All right, over here. Yep.
Mayra Osorio from Spain. Thank you for this wonderful talk. I would like to know which is the role of magnetic field. Can magnetic field prevent or favor planet formation? Could you say a few words about this parameter?
I don't know if I
Magnetic field.
Yeah.
Which is the role of magnetic field?
You wonder if it would affect migration? Is
Yes,
Oh.
in terms of the planet formation, can magnetic field
Okay,
favor
so
planet
planet
formation?
formation is chapter 20. In terms of migration, we do discuss what if the disk has a magnetic driven wind and how that would affect migration. It's similar to the dynamical co-rotation talk that I just discussed, but in this case, it's a disk that is moving rather than the planet. So that is in the chapter.
All right, thank you. Bertram.
Yeah, hi, Bertram Bitsch from the Max Planck Institute for Astronomy in Heidelberg. I wonder about two things when you compare the simulations to the observation. One is the accretion of gas onto the giant planet that could actually help you to open gap and erode the bumps that you generate when you dump the planet in. And the other one is actually related to the time scales of how you introduce the planet into your disk system, because the disks that you observe are a million years old and you normally do this in a much shorter time.
Right, both are excellent questions. So gas accretion onto planets have been attempted in some simulation, but most often not. So most of the simulation will show the planet is just a passive point source sitting there and doesn't accrete. So if it does, then presumably it would generate heating, and that would cause thermodynamic effect in the gap, and that could have additional effect on the gap formation, which is part of the additional physics that we need to explore. And what is the second question?
About the time scales, how long you introduce the planet compared to the lifetime of the disk.
Right, that's again, excellent question. So, simulations typically run for a few hundred to a few thousand orbit, and very often they're not as long as a disk lifetime. So if that's indication, if you say those some of the features may be transient, that could be true. And we don't know if the features we see in those disks are particularly long-lasting. They could be just present there for a period of time. Yeah.
Thank you.
Okay, two more questions. I think this microphone followed by this one. Yeah, so you first.
Thanks for wonderful talk. This is Yinhao Wu from University of Leicester. I noticed you don't seem to mention runaway migration. So let me ask, what you think about this migration?
Runaway migration, so there are two versions of runaway migration that we described in the chapter. One is type 3 migration. It's not in any one of these regimes because technically it could show up in any of the regimes where the planet is massive enough to make a dent in the disk. Type 3 can happen. That's all I can say. I don't actually know which regime it fits into. And then the other type of runaway migration happens with the dynamical co-rotation torque when the feedback is positive. So the planet is moving to a region of lower vorticity. And that is definitely something that can happen. Just given the planet is moving outward in the first place, that will just happen. And in the paper that we cite over here, I think Paardekooper 2014, there's a detailed description of the conditions that would lead to that.
Thank you.
Final question. Thank you very much.
Hi, I'm Shoji Mori out of University of Japan. Thank you so much. Very nice talk. I want to asking about the synthetic observation for the
observation with the narrow narrow ring structure, and then to reproduce the observation, what kind of information can we get from compared to the what kind of new information can we get compared to the previous kind of observation only with gap?
I think those narrowly packed rings and gaps is a new thing, sort of a new thing we realized in the past few years that indicates the presence of small planets, sub-Jovian, Neptune-ish mass planet in low viscosity environment. So that's the new, that's something new with those multiple narrowly packed gap and rings.
Are these information degenerated, or can we get constraint information?
The constraint on what parameters?
Yeah, kind of alpha viscosity or something.
Right. So to produce those rings using the mechanisms I described, you need viscosity or turbulence level to be relatively low. Yeah.
Okay, thanks for the questions, everybody, and let's thank the speakers again for an excellent talk.